Hello and welcome back to the Quantum Information Reading Seminar, where our goal is to read and understand the paper Black Holes as Mirrors by Hayden and Preskill. Last time we left off having looked at the consequences of the main inequality of the paper, and our goal today and in the coming remaining videos is to go through the rest of the paper and extract what we can from the paper. So already taking a look ahead, I have drawn a couple of conclusions about how the rest of this video series will go. So I can certainly confirm that we will not be able to go through in extreme, exquisite microscopic detail through every aspect of the coming pages of this paper. It's simply impractical to follow all the links that are coming. In particular, there is an extraordinary amount of physical intuition that has gone into the latter part of this paper, and a large amount of discussion which occurs variously at a rigorous and non-rigorous level. So this paper opens so many doors, it's very difficult for us to actually breadth first or depth first search through all the doors that are opened by this paper. And instead, what we'll do is we'll change the tone of these videos and step back from proving every single equation here and more zooming out a little. We started the whole video series with a sort of wide, broad overview. We zoomed in and got into the details of the proof of the main inequality. Now we're going to zoom out over the coming videos and discuss things at a higher and a less rigorous level. And by the end of this videos, we will probably only lightly skim over many of the topics that are opened up in this paper. So we left off last time looking at a heuristic analogy for the result of the paper. And now as we continue, we will start comparing our conclusions that we've obtained in this section with the classical analog that was introduced at the beginning of the paper. And so I'll continue reading where we were. As in the classical model, our conclusion can be usefully restated in terms of known results in the theory of noisy channels. For the quantum erasure channel with erasure probability p, the entanglement-assisted quantum capacity is q equals 1 minus p. Okay, so that needs a little bit of clarification. We've met the terminology erasure channel. What is the erasure channel? So the erasure channel for a qubit is a quantum channel, which means it's a completely positive trace-preserving map that takes a qubit state and outputs the following state of a qubit, or a three-level system. So this is important. An effective three-level system is the output of the erasure channel, not a qubit. So with probability p, the channel models the loss of the qubit state. And how do you model loss in quantum mechanics? By the full trace operation. So we lose the system. So with probability p, we lose it, but we know we've lost it. There's a signal state that tells us that the state is lost, and we call that state 2. 2 is an additional third level that was introduced in this definition of this channel. And with probability 1 minus p, nothing happens, right? The original state goes through. So that's the erasure channel, and it models the process whereby we lose a quantum state. A full qubit is lost, but we know that we've lost it. A signal is given to us that the state is lost in the form of this signal state 2. 2 is orthogonal to the qubit state 0, and it's orthogonal to the qubit state 2. It's an additional effective third level that's introduced to model the signal that we've lost the quantum state of the qubit. And here they're asserting that for the quantum erasure channel with erasure probability p, which I've just defined, the entanglement-assisted quantum capacity is QE equals 1 minus p. So we can, I will say what the entanglement-assisted quantum capacity is. That's, I'm not even going to really go through the full definition, I'll just say it in words. We suppose that we have Alice who communicates with Bob using this channel. we have a large number of repeated uses of this channel at our disposal, and we ask effectively how many qubits of information can we get through this channel, given that that Alice and Bob pre-shared effectively infinite entanglement. So although they've pre-shared infinite entanglement, that doesn't mean they can communicate. They need still to send some information in order to communicate with entanglement. Just because you measure an entangled state doesn't mean you actually communicate. Pre-shared entanglement doesn't immediately imply that Alice and Bob have infinite channel capacity. They can't communicate any information until they use a channel to do so, and that channel is in the form of this erasure channel. And so it's a known result and quite a classic result in quantum information theory that the entanglement-assisted quantum capacity is 1 minus p. What does that mean? It means that given that Alice and Bob have infinite pre-shared entanglement, that they can effectively communicate. So we suppose we have n channels here, n copies of the same channel, n uses of the same channel. They can effectively communicate. Alice can effectively communicate a fraction 1 minus p times by n qubits using n instances of this erasure channel. So this is a known result, classic result, quantum information theory, well worth looking it up. And they're going to relate this result to what we've discussed and described already in the context of black holes. So in our setting, the n minus k minus c qubits retained by the black hole are in effect erased as far as Bob is concerned, right? Bob doesn't get those qubits. They're gone. Alice chucks them in, they're gone. Yet Bob is able to extract k qubits of high fidelity quantum information. The quantum communication rate, R, which is effectively the number of qubits per channel usage that you can get through the channel, is achieved by using a randomly chosen unitary encoder and by exploiting a supply of pre-existing quantum entanglement that Bob shares with the black hole. So this is the pre-shared entanglement that we have back up here in this picture that Bob shares with the black hole. It's here in the left-hand side of this diagram, this blue entangled pairs, and that's the equivalent of this pre-shared entanglement in the Alice-Bob entanglement-assisted communication scenario. Suppose, on the other hand, that Alice is more cautious and deposits her sensitive quantum information in a relatively young black hole, so that the size of the E system is much, much, much smaller than Bob's system. In that event, the previously emitted Hawking radiation E will be nearly maximally entangled with a subsystem of B. The radiation will continue to be essentially featureless, revealing none of Alice's information until a certain moment, namely when B prime is effectively equal to the size of N, R, and E, right? Let's go back and remind ourselves of what N, R, and E are. So here's N is Charlie's reference system, R is the radiation emitted, and E is the pre-existing radiation that has come from the black hole. Soon after, the black hole will be nearly maximally entangled with its surroundings, and equation 6 will begin to apply. So equation 6, if you recall, is this main inequality here, the one that we worked rather hard on to prove. At that stage, Alice's information suddenly spills out. Here too, the conclusion is related to a well-known property of the quantum erasure channel with erasure probability P. Its quantum capacity unassisted by entanglement. So there's really a fundamental difference between capacities of quantum channels with and without pre-shared entanglement. So in the case where Alice and Bob pre-share so the picture we have here is that Alice is there, Bob is there, and they pre-share an infinite entanglement, and then Alice uses her channels to communicate to Bob, and then Bob does some kind of decoding operation. That scenario can and does lead to different capacities when we don't allow Alice and Bob to pre-share entanglement. In the case that Alice and Bob is not allowed to share pre-share entanglement, then Alice can't use that to help Bob to decode, right? And so the two rates effectively the number of qubits you can communicate from Alice to Bob can be very different. And here another classic result in quantum information theory is that the unassisted entanglement capacity is really zero. It's not 1 minus p, it's exactly zero for p is greater than a half. So when you throw, with 50% probability, throw a quantum state in the bin, then you have no quantum capacity. And when when the erasure probability is less than a half, then there is some quantum capacity. So if the black hole initially holds n qubits, then when n plus k over 2 qubits have emerged, n minus k2 qubits remain inside the black hole. At this point, Bob's system is k qubits larger than the black hole, so that Bob has acquired k qubits of quantum information. Thus, the communication rate is r is k over n, and the erasure probability, the effective erasure probability that we have here, is a half minus r over 2. So now the authors are going to relate this to something that's been observed, a classic result in the theory of black holes and quantum gravity due to Don Page. So some years ago, Don Page observed that the information swallowed by a black hole remains hidden until half of the black hole's qubits have been radiated away, and then emerges at a constant rate as the evaporation proceeds. So this is an absolute classic result in the theory of black holes. Equation paper 12. Average entropy of a subsystem, 1993. Well worth checking that out. But what this paper does is it goes a little bit further than Don Page's paper. See, they explain this as follows, right? Our conclusion is similar, but our analysis goes further. Page considered the time dependence of the quantum entanglement of the black hole with its surroundings. And so what Page found, you sort of draw a plot. Is that as time proceeds, that the entropy or the entanglement of the black hole with its surroundings starts out low, goes up high, and then goes down. It's the so-called Page curve. We have focused instead on when a fixed amount of quantum information of particular interest can be recovered. So there's a big fundamental difference between this so-called Page curve, which describes just how the entanglement of the black hole and the rest of the universe depends on time, and what Hayden and Preskill are doing. So what Hayden and Preskill are doing is they imagine that you add a little bit of entanglement, you throw some information in at some earlier time, and that's in the form of entanglement with the Charlie's reference frame, effectively. And then that, of course, throwing that information into the black hole leads to an increase of the entanglement of the black hole with the rest of the universe. And then they want to track where that information goes, right? So instead of just saying how the coarse entropy of the whole object is changing or the coarse entanglement is changing, they want to track the entanglement due to those particular qubits that were thrown in at Tn, those k qubits, right? And so as this information is somehow diffusely spread throughout the black hole, and then at some point, as the black hole starts radiating information, those qubits that are smeared up and mixed around in the dynamics, they somehow escape, right? And Hayden and Preskill's goal is to really have a much more fine-grained understanding of this decay of, let's say, really the decay of entanglement, and when this entanglement that comes out can be said to have contained those k qubits. And our simple model of quantum black holes leads us to two main conclusions under the assumption that Bob has unlimited control over the Hawking radiation. Of course, and this is an important point, if Bob does not have control over the Hawking radiation, he hasn't built this huge sphere around the black hole, then there's no way he can recover Alice's hidden information. I mean, that'll just fly off at the speed of light, never to be recovered again. So if Alice dumps k qubits into the black hole after half of the black hole's initial entropy has been radiated away, the information bounces right back. So that's really one of these fairly general conclusions of this paper, is that under pretty mild assumptions about the dynamics of the black hole, namely that it has some pretty complicated dynamics, which sort of naively seems fair, that generically information dropped in after the halfway point here, t halfway, that information will just bounce straight back out. So that's the really striking conclusion of the Hayden and Preskill argument. And Bob recovers because Bob's monitoring the radiation coming out of the black hole. Bob can really get that just after a few units of time. On the other hand, if K dumps the information into the black hole before the halfway point, then Bob needs to wait for a while. He in fact has to wait to the halfway point. But once the black hole reaches the stage where half of its qubits have been released and the black hole has become maximally entangled with its surroundings, Alice's information pops out immediately. So this halfway point here in the evolution of the entanglement of the black hole is a crucial moment in the role. It plays a crucial role in determining when information becomes exposed or not exposed. So both statements seem strange upon first hearing, but especially the latter one, because who is to say which K qubits are Alice's? So this is a very strange thing, right? You know, this black hole radiates a handful of qubits, I mean more than K, but not lots more than K, and then all of a sudden Bob can extract Alice's qubits. Like, why did the black hole choose to radiate exactly Alice's qubits at that epoch? That's why this statement sounds strange, right? It's as though the black hole knows that Alice's qubits are the ones we want past the halfway point. Well, now the authors go on to point out a very interesting observation. So in fact, no matter which K qubits of quantum information swallowed by the black hole are of particular interest, these K qubits are revealed almost right away when the half point of evaporation is finally reached. And this is the really remarkable physical consequence here. There's nothing special, they say, about the subsystem M of B that is maximally entangled with N in figure 1, right? So N is Charlie, here's N. Charlie's entangled with some effective subsystem M that then gets smooshed up inside the black hole and then apparently released at the halfway point. But, you know, why did we focus on those particular K qubits? There could be other Alices out there who also want to throw their diaries in the black hole. And why is our analysis special to this particular Alice? Well, the answer is it's not. This is a generic result. There is nothing special about the subsystem M. For any other K qubit subsystem, the conclusion would be the same. There's nothing special about the Alice that we've been looking at so far. That N becomes very nearly maximally entangled with a K qubit subsystem of Re. So this is a key point about this whole analysis. It's essentially independent of who throws their qubits in the black hole. So when we have a black hole that initially held N qubits, has evaporated past the halfway point, so that only N plus K plus C qubits have been emitted, Bob gets to decide which K qubits of information he will retrieve from the Hawking radiation. When he makes up his mind, he performs the decoding operation on the radiation, the pre-emitted radiation and the post-emitted radiation, and he maps those K qubits to the quantum memory in his laboratory. But there is a catch though. Bob can recover almost any K qubit system, but he cannot recover more than K qubits. So the information's there, it's buried in the radiation. Let's go back up here. So the information is there for any arbitrary K qubit system. But should Bob choose to extract one particular K qubit subsystem from this radiation, he is then blocking himself off from extracting information about any other K qubit system. It's an exclusive operation. Returning to the situation depicted in figure 1, imagine two different K qubit subsystems of the black hole, one called M1, purified by the reference system N1, and M2, purified by the reference system N2. When Bob decodes only M1, his decoding map is permitted to act on N2, right? He is allowed to act on that subsystem, which is now considered to be part of the radiation subsystem, RE. And when he decodes only M2, his decoding map may act on M1. But if he greedily wanted to decode both M1 and M2, then both N1 and N2 would be out of his reach. Thus, trying to decode M2 in addition to M1 only interferes with his ability to decode M1. So the information's there, you're just not allowed to access it. He'll have to wait for the black hole to emit more quanta. We note that if the internal dynamics of the black hole is actually time reversal invariant, then it may be more appropriate to model the dynamics by choosing the matrix VB either from the circular orthogonal or circular symplectic ensemble with a choice depending on the total spin of the black hole. Okay, now we've moved from this general and striking consequence to some very specific. So yeah, we can now sort of pause for an aside. So time reversal invariant dynamics versus dynamics, right? General. So, I mean, so far we modeled the dynamics of the black hole. We model it with just a unitary, an arbitrary unitary. Nothing special about this unitary. However, time reversal invariance takes a unitary and gives us its complex conjugate effectively. It's an anti-linear operation. And we demand that our dynamics is invariant under this operation. And in that case, U can't be, so if T U equals U bar equals U, since time reversal invariant, then U is not allowed to be a general unitary anymore. It's no longer allowed. U has to be, well, in this case, an orthogonal matrix, right? Because if you have a real matrix that when you multiply it by its adjoint, you get the identity, that just means orthogonal. And so they're making a comment here in a parenthetical remark that should we demand that the black hole has extra symmetries, such as time reversal invariance, we should, in fact, be a bit more careful about what ensemble we chose our dynamics from. So the circular orthogonal ensemble, for example, or in the case of, depending on the spin, maybe the circular symplectic ensemble. So different random matrices. And they feel here that time reversal invariance is not a fundamental symmetry in nature. In particular, you just think about the expanding universe. It is sensible to consider V chosen with respect to the Haar measure on U2n, namely just a completely random unitary matrix. However, were we to insist on time reversal invariance or some other discrete symmetry like that, then they claim, and I do believe, that the conclusions would be more or less the same. That's because the integrals that we had to do to evaluate this bound, they have very, very similar the form and similar values for all these random matrix ensembles. So it's really pretty much independent of the kind of dynamics you assume for the black hole, as long as it's sort of sufficiently complex enough. Okay, and we're going to use that, I think, as a transitionary sentence to go into the next part of the paper, which talks about the thermalization time of the black hole. So far, we've just assumed that the black hole's dynamics, here's the black hole, in comes the qubits, and then sort of, and at some time t, and then at a time t plus epsilon, some infinitesimal time later, then the qubits with the pre-existing qubits of the black hole undergo a completely random unitary, like that, right? Super quick. The black hole's dynamics just act essentially instantaneously on infalling qubits. And that's, questionable, right? We don't expect that things happen instantaneously in nature. And here in section 4, we're gonna consider timescales. How long does it take, really? How long should we allow the black hole, or how long should we think of the black hole as taking to actually fully carry out a unitary dynamics according to some very complex random unitary U? So here we go. We're going to, in section 4, spend a little time dwelling on these assumptions and perhaps justifying them and putting numbers to the timescales that are really involved in black hole dynamics. And so we come to the section 4, the thermalization time. As for our classical model, there are some non-trivial assumptions underlying our model of a quantum black hole. Yes, right? In particular, when we conclude, in the case where the black hole is maximally entangled with the previously emitted radiation, that Alice's information comes out fast, we are taking it for granted that the information deposited by Alice is rapidly thermalized by the black hole's internal dynamics. So that's exactly what I said before, that in an infinitesimal instant of time, the unitary U is applied to Alice's qubits and the qubits internal to the black hole. By rapidly, we mean on a time scale comparable to the time interval between the emission of successive radiation quanta. So the time scale is compatible with the interval between the emission of successive radiation quanta. So in terms of the Schwarzschild time measured by static observers who are far from the black hole, this interval is ordered the Schwarzschild radius Rs for a non-rotating uncharged black hole in units where the speed of light is c1. So there's one length equals time scale in this problem, and that's the radius of the black hole, right? We have essentially nothing else to describe the black hole with. It's not rotating, it's not charged, so this doesn't give us any kind of unit scales. And since c is 1, length is time, the radius really determines for us also a time scale. And now they're going on to just discuss this Schwarzschild radius and the time scale that it implies. So there are several reasons why Rs might seem at first to be a reasonable estimate of the black hole's thermalization time. So what we're to gain here is that they're foreshadowing that Rs is not the right time scale. That's clearly what's being foreshadowed here. But first they're going to tell us why you might think it is. So classically, perturbed black holes have damped quasi-normal ringing modes where the damping time is comparable to Rs. So, if you hit or disturb a black hole, namely by smashing, say, another black hole into it, then these things ring down, and there's a time scale for the black hole ring down until it sort of becomes, all these oscillations die out and it becomes completely static again, or effectively static. And we've seen sort of pictures of that in the recent observation of gravitational wave emission from black binary in spiral mergers of black holes. And so that is a very natural timescale to think about, right? It's a timescale determined by the black hole. You throw something, you kick the black hole, it vibrates a little, and then it rings down. And you can probably, it's very natural to think that that's the timescale for the black hole to forget about this kick. Furthermore, under the ADS-CFT duality, the joule of a large black hole is a strongly coupled conformal field theory with the same temperature, T equals 1 over the Schwarzschild radius. And in the field theory, the only relevant timescale governing the approach to thermal equilibrium is indeed the timescale set by the temperature itself. 1 over T is Rs. Thus, if one kicks the strongly coupled thermal bath, Rs is the timescale for the bath to forget about the kick. If you have a cup of hot coffee and you drop a droplet of some cold water in it, then that'll diffuse through the thermal bath until the bath comes to equilibrium again. What's the time scale? Effectively the inverse temperature. So this is all, okay, I find the first part of this argument more convincing than the second half, right? So we really can talk about the quasi-normal modes of a black hole within general relativity. That's something you can study. You just study perturbations to the black hole horizon and see how they evolve under Einstein's field equations. that you can do, right? And that's a perfectly legitimate calculation. The second, and there, these timescales are extremely natural there. And then secondly, under this ADS-CFT duality, there you have to accept the hypothesis that in ADS space-time, right, we're talking about a different space-time to the flat space-time that's sort of implicitly spoken about here. In ADS space-time, then there is a way to describe black holes by a dual complex quantum system, a conformal field theory, and there that just adds, say, further evidence for this naturality of this timescale. However, when one says that the strongly coupled quantum field theory thermalizes in a time of order 1 over t, one ordinarily means that the system relaxes to a state that is locally indistinguishable from a thermal state on this timescale. That's a key point, right? When a system thermalizes, or when this black hole rings down, you would say that timescale is that's determined essentially by our macroscopic ability to observe the system. And that's what is meant by locally indistinguishable here. We can't measure the position of every particle or atom or molecule in a cup of coffee. And so we are convinced that that system has thermalized when we can, with just our eyes or a thermometer, no more tell that system is out of thermal equilibrium. If, however, we were to look at the microscopic state, the microstate of the system, we might not say that the system has thermalized. It's only locally looking, from an outside coarse perspective, does it look thermalized. And they're making exactly the same point here about black holes. When the black hole is rung down, does that really mean that it's rung down, or just that with our telescopes, that when we look at the black hole, it's no longer moving, but internally all the microstates are in motion? So our assertion that information captured by a black hole is quickly re-emitted in the Hawking radiation rests on the validity of a more general, stringent, global criterion for thermalization. How long does it take for the quantum information deposited by Alice to become thoroughly mixed with the black hole's microscopic degrees of freedom? So here we have this the difference between microstates and macrostates. So up to now, the Schwarzschild time is more a statement about macrostates of the black hole. And now we want to get right into the microstates. What are they doing? And to what extent is this timescale the same timescale here? So since this is really a question about strongly coupled quantum gravity, we don't actually have the tools to answer it. So we can't answer that question at the moment. But we can make a plausible guess. And it's, we have to accept that we can't reason about this system. We don't have yet a completely finished theory of quantum gravity. So we have to reason indirectly, just as we reasoned indirectly about quantum mechanics in the turn of from the 19th to the 20th century. But that doesn't stop those reasonings from being helpful for the development of a quantum theory. So for this purpose, we envisage the black hole's qubits as uniformly distributed over the stretched horizon. So what's the stretched horizon, right? So we have a black hole and we have the horizon of the black hole, and that's what we know what that is, right? That's where you can't get back out again. Now, a stretched horizon is an idealized concept. It's the horizon that's exactly sort of one Planck length. It's a sphere surrounding the black hole, exactly one Planck length, hovering a Planck length above the actual horizon. And you might, it's an interesting sort of thing to think about. If you're a Planck length away from the horizon of a black hole, then you can pretty easily tunnel into the black hole and never get out again. So it's somehow effectively, you're within an uncertainty principle of actually being in the black hole. So the stretched horizon is located about 1 Planck unit of proper distance above the actual global horizon. Here, static observers have a proper acceleration of order 1 in Planck units. So they feel the gravitational field of the black hole and they're accelerated. Therefore, are surrounded by a bath of unruh quanta with temperature of order 1. So this is the radiation from the black hole, coming out with this ray, and you are just above the horizon. Quanta from this bath are directed nearly radially outward, can escape to infinity as Hawking radiation with a redshifted temperature of order the inverse Schwarzschild radius. So now we come to, we're going to try and make plausible arguments about the black hole, but in order to do so, we're going to have to accept further hypotheses about the quantum mechanics of black holes. And in particular, we're going to have to accept a hypothesis known as the black hole complementarity. So black hole complementarity, introduced by Susskind, maintains or holds that observers who remain outside the black hole may legitimately regard the stretched horizon as a repository that stores quantum information absorbed by the black hole, even though the strongly coupled Planckian soup is invisible to free-falling observers who pass through the horizon. Okay, so you're an observer outside the black hole, and you can see the stretched horizon. It's just this Planck unit above the horizon. And in black hole complementarity, we're allowing that observers who remain outside the black hole will regard this stretched horizon as storing the information that was absorbed by the black hole. Because of the high temperature of the Planckian soup at the stretched horizon, we need a thorough grasp of quantum gravity to understand its detailed dynamics. So because it's so close to the horizon and it's subject to the laws of quantum mechanics, it's some roiling sea of particles. And in order to properly describe things at the stretched horizon, we really do need quantum gravity. And here's why we even, and therefore, as a concept, maybe it's useless, but the point is, it's not completely useless for reasoning about the dynamics of black holes. And here we come to the point where it's not useless. So the stretched horizon has some dissipative properties that can be analyzed classically. For example, if electric charge is deposited in the black hole, currents flow on the stretched horizon to redistribute the charge, right, which are damped by the stretched horizon's internal resistance. So the picture I guess I have in mind now is that some charged particle comes in. Here it is, with some charge Q. It gets absorbed by the black hole, but remember we're an observer outside the black hole, so we're allowed to regard the stretched horizon as somehow being the information about what was absorbed, as containing this information. So this charge Q sort of sails into the black hole, but our last snapshot of it essentially is at that stretched horizon, and that leaves localized charge in the neighborhood of the horizon and on the stretched horizon. And then very quickly the dynamics, even at a semi-classical level, will act to redistribute this charge over the stretched horizon. That's what we've got to understand here. And how quickly, so charge doesn't instantaneously travel from point A to B, and we've got Ohm's law to deal with. So this is the current is determined by the resistance. So the local charge density, and that's what they say here, I guess. So electric charge is deposited in the black hole, currents flow on the stretched horizon to redistribute the charge, right? The charge, what we know about black holes is that they don't have a localized charge density structure on the boundary. The black holes have a charge, and it's sort of equally distributed over the entire boundary of the black hole. And so the black hole is going to want to redistribute that charge that I initially localized at this point here all over this boundary of the black hole. And how long does that take? The local charge density decays like x minus t over rs, where t is the Schwarzschild time, and correspondingly the proper area of a droplet of charge on the stretched horizon grows exponentially fast, right? It's got to redistribute this droplet here until it's a uniform thin layer around the entire black hole. And how long does it take? Well, e to the minus t over rs, which means that area of the droplet is going to rapidly grow. The droplet envelops the stretched horizon, and the charge distribution reaches a new steady state after a Schwarzschild time of order rs log s. Right? So it's got to travel around the horizon. It's traveling really fast. That's what this exponential is telling us, but it's still got to get around the horizon. Therefore, that's why we've got this rs log s. So from the perspective of static observers hovering above the stretched horizon, the spreading of charge is very fast, reaching a proper distance of order rs in a time of order log rs as measured by their clocks. Yet these observers are unable to manipulate the flow of charge to achieve superluminal communication, right? So this charge, it sort of it goes around the black hole effectively faster than the speed of light, but we're not able to manipulate the flow of charge to achieve superluminal communications. This is a key sort of feature of relativistic scenarios, is that you can often build situations where it looks like information is traveling, where things travel faster than the speed of light, but when you try and exploit that phenomena to send information, that's what doesn't travel faster than the speed of light. So you have to bear in mind that what relativity precludes is the communication of information faster than the speed of light. So although the charge redistributes rapidly around the black hole horizon, we can't exploit that as a static observer hovering above the horizon to achieve superluminal communication. So this is at least the claim here. So in its classical realization, the superluminal spreading of electric charge at the stretched horizon is really a kinematic effect. It has actually nothing to do with dynamics, apparently. It arises because the static observers in the Schwarzschild geometry separate with constant proper acceleration from the freely falling charged particles beneath the stretched horizon. So these particles are, I'm an observer, a static observer above the black hole. Here's the black hole here, and here's the observer, and then here's this charged particle Q, and I'll draw time coming up here. So the black hole is actually sort of a black cylinder. Here's the world tube of this black hole, and here's the world line of the observer, the blue line, and here's the charge, Q, a little blob of charge. It falls into the black hole, and then these two trajectories start separating rapidly, and they separate with a constant proper acceleration, right? They're just accelerating. And they're plunging toward the black hole's global event horizon. One feels hesitant about drawing any far-reaching dynamic conclusions based on this kinematic spreading. But on the other hand, a complete physical description of physics at the stretched horizon should accommodate some kind of rapidly mixing dynamics, making it hard to distinguish between effects that arise from strong local interactions and effects that are merely kinematic. Thus, one is tempted to postulate that the exponential spreading, we're not even going to postulate, right? We're tempted to postulate that the exponential spreading is exhibited not just by the black hole's classical hair, but also by its quantum hair, i.e. the quantum information that it encodes. So this horizon encodes quantum information, that's its hair. So to the observers anchored at the stretched horizon, not just the local charge density, but also other local disturbances of the thermal bath decay, like this, very rapidly, like this e to the minus t stretch, where t stretch is the time in Planck units as measured by static clocks at the stretched horizon. So now they're going to tell us that not only charge distributes itself rapidly over the surface of a black hole, but other quantities. In particular, I assume we're going to get to the hypothesis that any quantum information whatsoever, any local density of quantum information is going to distribute itself rapidly over the horizon. If we somewhat fancifully envisage information deposited in the black hole as a locally conserved fluid, so you can somehow think of qubits as a fluid, the information carriers of quantum information, they have to be particles of some kind, or quanta, or radiation, quanta, but in particular there has to be a physical carrier of the quantum information. So it's not so ridiculous to think of them as a locally conserved fluid, like, instead of a fluid of electrons, we have, radiation or whatever, the polarization. So this information suggests that this image of information as a locally conserved fluid suggests that the droplet of information, just like the droplet of charge, expands exponentially and becomes nearly uniformly distributed over the stretched horizon in a time order log of the Schwarzschild radius, corresponding to the Schwarzschild time Rs log s. So this picture leads us to suggest that the black hole's global thermalization time is actually Rs log s. In a sense, this suggestion, also put forward at 9, only deepens the information puzzle, as it poses the challenge of reconciling the rapid spreading of quantum information on the stretched horizon with the black hole's causal structure. So, it's really stretching relativity to think that this information redistributes itself so fast around the black hole's horizon, because that seems acausal. On the other hand, rapid distribution of many particle quantum entanglement need not imply superluminal signaling. This is a key point that I also alluded to earlier. Just because you found a mechanism whereby some quantity appears to travel faster than the speed of light, if that doesn't entail any information spreading faster than the speed of light, then that is totally allowed by relativity. Furthermore, the black hole complementarity viewpoint already postulates that the semi-classical causal structure of a black hole must be highly misleading in some respects. The superluminal spreading around the black hole horizon is a relatively gentle extension of a viewpoint we are already taking for granted. If an observer who is a distance of order Rs from the horizon drops a freely falling quantum memory into the black hole, it takes Schwarzschild time of order Rs log s for the memory to reach the stretched horizon, and conversely, it takes Schwarzschild time of order Rs log s for quanta emitted from the stretched horizon to reach the observer's detector. Therefore, a thermalization time of order Rs log s is in fact compatible with our central metaphor, that the black hole is a mirror in the sense that it returns Alice's information in a time comparable to the time it takes the information to fall into the black hole. So the picture now that I'm drawing from this whole story is, instead of Q here representing charge, Q here really represents qubits. They land, they accelerate to the stretched horizon, they redistribute rapidly around the black hole, and then they're re-emitted. And that all takes time of order Rs log Rs. Now, the black hole is a mirror in that sense. So if one more conservatively insists that the spreading of a droplet of information remains confined to the forward light cone, then the time required for global thermalization is T stretch is omega Rs, corresponding to the Schwarzschild time T is Rs omega, big omega Rs squared. So here, what is this big omega notation? I never remember this. Indicates a lower bound on the thermalization time for asymptotically large Rs up to a multiplicative constant. In that event, so here we got the T stretch is bigger than some constant times by Rs. Yeah, right. So, T stretch is the time scale that's relevant here is Rs log S, log Rs, and that's, we always have an upper bound to that, a lower bound to that quantity. Let's go back to the paper and see what's being said here. The time required for global thermalization is T stretch equals big omega Rs, corresponding to the Schwarzschild time T is big omega Rs squared. Here the big omega notation, blah, 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 up to a multiplicative constant. Okay, so this is... We're conservatively requiring that this... so here I think they are making a more restrictive assumption about how this quantum information distributes itself over the horizon of the black hole. They're saying instead of it being superluminally spreading itself over the black hole horizon, we demand or insist that it still is bound by the speed of light as it distributes itself over the black hole's horizon. So even if we do that, then the thermalization time is still Rs, and the corresponding to now a Schwarzschild time of T equals Rs squared, roughly speaking. In that event, since global thermalization is achieved, k qubits can escape in Schwarzschild time T equals kRs. One may expect that the Schwarzschild time for a constant number of qubits to escape from the black hole is T is roughly Rs to some power times by log to some other power. Okay, I think we're just going to accept this. And here we are saying that P and Q are sensitive to whatever model you have for how quantum information distributes over the quantum black hole's horizon. So of our two main conclusions in section 3, the conclusion that Alice's qubits bounce right back if the black hole has already radiated more than half of its initial entropy really does require rapid thermalization, i.e. thermalization in this rapid Schwarzschild time t. I said that differently. Of our two main conclusions, the conclusion that Alice's qubits bounce right back really does require rapid thermalization. Because in particular, that we can understand without really thinking too deeply about the dynamics of black holes. If it takes ages for the quantum information that Alice throws in to interact with all the little qubits, microscopic degrees of freedom of the black hole, then there's no possibility for that to bounce back out before it's had time to have that interaction. But the other conclusion, that previously absorbed quantum information is released quickly when the evaporation reaches the halfway point, still applies even if thermalization takes much longer. For the second conclusion, we only need thermalization to be fast compared to evaporation, which occurs in a Schwarzschild time order RS3 rather than RS log S. Okay, so we are about done for today's discussion of the paper. Now, we have moved somewhat quickly over the content of section 4, and I will justify this in two ways. So firstly, there are relatively few equations that we can engage with in this discussion. And secondly, we have to take on board a large number of assumptions, plausible or not, in order to even talk about the dynamics of a quantum black hole, the quantum dynamics of a black hole. Now, it's up to you whether you believe these assumptions are indeed plausible or not. And I didn't pursue the references to prove any of these statements here. So we didn't spend, I just flew over statements like how long these timescales are, how big these timescales are. And the reason that I did that is that were we to really want to go through all the references and prove, or at least make plausible those calculations, we'd have to do the calculations. And so I can see that now we reach our own horizon of sorts in reading through this paper. If we're going to pursue every one of these statements and try and understand it and justify it, we will be grind rapidly to a halt. So instead, I've adopted the attitude in reading through this section that we will just be will benevolently accept all the statements made, and take that as just a list of assumptions and then conclusions. So if we just accept without challenging or uncritically accept these assumptions that are listed here, then we can draw these conclusions. And the conclusions are relatively simple consequences of these assumptions that we've, this list of assumptions. Were we to insist on a more detailed justification, then that would carry us through into a much larger discussion, which I think is a worthwhile and fascinating discussion to have, that will in particular take us into the intricate dynamics, semi-classical dynamics of black holes. Now that's well beyond the scope of this paper and the discussion of this paper. And so for that reason, we're going to satisfy ourselves here with this somewhat superficial reading through of the content. And so if I have to now summarize in a nutshell what section 4 is saying, section 4 tells us that black holes thermalize on a particular timescale, RS, and that the microscopic degrees of freedom of the black hole thermalize extremely rapidly. There are circumstantial evidence that that's the case, and that the full global thermalization time is somehow RS times by log RS. Okay, we will just accept that. That's how it is in this theory. And then in the coming video, we're going to move on to the topic of efficiency and actual resources required to encode and decode. And probably in a final video, we'll rapidly skip over the last couple of topics in the paper. But for now, that's it. Thank you very much for your time, and I look forward to seeing you next time.